Welcome to this class. So let us look at the case where the data is not linearly separable. SVM for right non-linear separability, it doesn't mean that it is separable with a non-linear decision boundary. Okay. Non-linear separable case, if I write it that way, it means that there is a non-linear separating hyperplane. It's not that, we'll consider that case later. So we'll look at the case where the decision boundary is still linear, but the data is not separable. So which means that there does not exist a W star such that you get 100% accuracy on data, right. So what do we do in that particular case is the question. Let us look at that. So this implies that there does not exist a W star such that yi times W transpose xi plus b is greater than 1 for all I. So remember how we got to this greater than 1 from 0, right. From greater than 0 we went to this greater than 1 by scaling it and all that, right. So this there does not exist a W, not W star, we will say it does not exist a W such that this happens. So now how do we formulate SVM in this case is the question, okay. Any ideas on how to do this? How do you tweak the SVM to accommodate this case? If you already know it, then fine. If you don't know it, you'll have to think. Yeah, not kernel yet, right? We'll go to the kernel case where the decision boundary itself is not linear. Think about it first. I mean, for people who does not know what we are doing it, right? Think from first principles. What we are saying is that there can exist cases, or there does not exist a separating hyperplane that give you 100% accuracy. So what do you do is the question, okay. The way to do it is introduce another additional variable into optimization. That quantifies the extent of misclassification. See, if the data is not linearly separable, and remember that we are still looking at the case of linear discriminant functions. The discriminant function is still linear, but the data is not linearly separable. This means that we are going to make mistakes, right. Now what should we do is that we will have to find a decision boundary that would minimize the mistake in a sense, right. That is what we should do. So to quantify the mistake that that this decision boundary is incurring, we will have to introduce another variable into the optimization, okay. Now how do we do that? So we have, the original problem was as follows. Original problem was that you minimize half W transpose W, maximize the margin subject to W transpose xi plus b was greater than 1, correct. This is what the original problem was. Now on a data point xi, this decision boundary can make a mistake, because I know that for all x I cannot, for all xi I cannot find a W such that this happens. Now suppose it makes some mistake. So what I will do is I will add or subtract that mistake from this, okay. Now suppose for a data point xi, the product of yi times W transpose xi plus b is some value, okay, which is less than 1. Then what I do is I will subtract that value from this, that is it. That is what I incorporate in this variable xi. You understand what I am saying? So now think about it. For all data points for which xi is greater than 1, the discriminant function is making a mistake. Yeah. Okay. So here what am I doing is, let me write it geometrically, maybe then you will appreciate it much better. In case where okay, now this is not linearly separable, right? So let us say that I have a decision boundary here. Okay, this is the decision boundary. So now this is making mistakes on these data points, right? On these data points, the ones that are, it's making a mistake. So for every mistake that it does, these are the data points for which yi times w transpose xi plus b is not greater than 1 for these data points. Do you agree? Correct? But I mean, it is some value, right? It is not greater than 1, it is some value. So what is that difference? I am encoding that difference in this new variable called xi. Does it make sense? Right? So I have still not completely defined the optimization problem, you know, it's not complete yet, but did you understand what this variable is? Whatever decision, so remember that I am constraining my my choice of functions to linear discriminant functions. We have not gone to the case where the discriminant function itself can be nonlinear. We are still looking at the case where the discriminant function is still linear. Now because the data is not linearly separable, no matter what line I draw, I am going to make mistakes, correct? And I am incorporating, I am codifying those mistakes by an additional variable called, I mean, which I have denoted by this xi. Okay. Now the optimization problem should have something to do with xi also, right? I need this to be minimum or max. We will see how to codify that, but you understand what this xi is for now. Any line that I write, that I draw, is going to make some mistakes, and those mistakes have been uh, accounted for with this new variable xi. That this is called the slack variable. We'll put all the constraints. We'll put the constraints. Yeah. Okay. Now we will talk about, as he said, no, we'll have to talk about constraints. So suppose I now solve the optimization problem. Okay. Okay. So first of all, my optimization problem now will have another variable xi also, right? We'll have to control this variable as well, because if we don't do it, then the optimization or the algorithm will take any arbitrary line and account all the mistakes in this xi. So we'll have to constrain, to put a constraint on that, right? Without constraining, every data point can be misclassified and all the misclassifications can be just designated onto this xi slack. We'll have to ensure this slack is constrained. So how do we do that is the question. So let us write that down. So unconstrained slack may lead to trivial solution. What is a trivial solution? Mathematically speaking, it can make w to be 0, make your w to be a 0 vector. So everything is misclassified, right? Okay, fine. I'll choose my xi to be minus xi or something, right? Or minus, adjust it that way in accordingly, so that all mistakes are accounted for, right? The trivial solution, for instance, w equal to 0. Okay. Therefore, solve a constrained version. Can you tell me what the constraints has to be? Huh? So we'll have to do some, we have to place some constraint on this xi. What can be a constraint? So I mean, what do we want slacks to be? As, yeah, minimum, right? We need as many lesser slack variables as possible, right? So first of all, we assume that all these are non-negative, because that's a choice that we are making, okay. So we will constrain that these have to be non-negative, and we will also say that the kind of the number of slacks that we need has to be as small as possible, because every slack is a is a correction for the misclassification, and we want the misclassification to be minimal, and therefore we will say that the slacks have to be minimized, okay. So how do we do that? We will do it this way. So you minimize W transpose W plus, so add some, yeah, let's W transpose W plus some C times sum of slack, and we want this to be minimized. So we are minimizing W transpose W, right, which is maximizing the margin. We want to find this discriminant function in such a way that the sum of slacks have to be minimized. So that's a non-differentiable thing, no? So you want something that can be differentiated. So, and we are assuming that these slacks are non-negative. Therefore, we can, it's minimizing the one norm that way, you know. Yeah. So minimize over W and xi. What do we have to do is that we will have to find this in such a way that the sum of slacks is minimized. And we also put this constraint, that the two constraints such that yi times W transpose xi plus B is greater than 1 minus psi I for all I, and we also want all these slacks to be non-negative. This is the problem that we solve. Hold on. A couple of observations before I take questions. The first observation is that those slacks, okay, which are between 0 and 1, slack variables for those data points for which slacks are between 0 and 1 will be those points which are correctly classified but within the margin. The one for which the slack is greater than 1 are the one that are misclassified. This is just geometrically this is how it looks like, okay. So now we, instead of solving the standard SVM problem, we will solve this particular problem, and this is called, this formulation is called SVM with slack variables, where we are accounting for mistakes. So here we are not assuming that the data is linearly separable, okay. Questions on this? Distance from the margin, no, this way, that's the slack now. The way we have done it geometrically, it is distance from the margin, yeah. And that's why the statement that I just made makes sense. Now if it's between 0 and 1, then it puts the data point between the decision boundary and margin. If it's greater than 1, then it is misclassified, okay. Shall we move on? We'll have to write the KKT for this problem now. Let's do that. Okay, I'll tell you what we are going to get now, okay. Yeah. Like, even if something is classified correctly, I will have a value, right? What have we put in the formulation of the slack variable that inhibits it from giving a value to things that are classified correctly? If it's just the distance from the margin. This one. We want it to be minimized, no? So the only way the sum of the slack can be minimized is by making it 0 for the points which are correctly classified. So we have incentivized the optimization problem to choose zeros for slacks as much as possible, and that can only be done if it is correctly classified. Yeah. So, I will tell you where we get into, right. We will see that the optimal decision boundary does not change, the equation for the optimal decision boundary does not change, okay. Even the dual problem does not change. With the slack formulation, there is only one additional constraint that comes on the dual problem, that is all, everything else remains the same. So, now if you put a additional constraint on the final QP problem that we solve, then you are implicitly solving the slack formulation, is what we will show now mathematically. That is why this is so elegant. So, even when we change we make such a big assumption that the data is not linearly separable, the final problem that we will be solving will stay exactly the same, but for an additional constraint. That is what we are going to show now. Okay, I will do the algebra quickly. Now, yeah, before we write the KKT, we will have to write the Lagrangian for the above problem, right. So, now Lagrangian will be a function of W B Lagrange multipliers mu, there will be another Lagrange multipliers lambda for this particular constraint, right. So, there are two constraints here, is equal to half W transpose W plus, close the door, C times 1 through n psi I plus mu I times 1 minus xi I minus yi times W transpose xi plus b minus lambda I xi I. Oh sorry, yeah, this will be a function of xi also, yeah, will a function of WB xi mu and lambda, that is what it is going to be. Lambda are the new Lagrange multipliers, okay, that we are getting for the newer constraint that we have. Is that okay? This one, right? Here there is no 1 minus because it is greater than 0 is what we are writing. So, the way the constraints are written are some some function of the optimization variable less than or equal to 0, and that is why there is a minus here, and that is why you have a minus here. Hold on, I will tell you, that is a good question. What is the role of C, right? It plays the same role as that of the regularization constraint. We will see that at the end of this class. Okay. So, we will have to write the KKT for this problem. So, the first one is the derivative of the Lagrangian with respect to W is 0, which will lead to the exact same solution that we had before. And if you take the derivative of this with respect to B and put it to 0, then there's a we'll have to now take the derivative of this with respect to xi as well, right. So, this will give rise to this one constraint, that mu I star plus lambda I star is equal to C. Okay, for all I, and we have the complementary slackness conditions, which would be constraints times Lagrangian multiplier is 1 minus xi minus yi times w transpose xi plus b is equal to 0, and lambda I times xi is equal to 0 for all I. So this is these two are complementary slackness conditions. Okay, these are the KKTs that we have. Okay, so please note that this, as I said, W star doesn't change, it just still remains exactly the same. We have this additional constraint that the optimal Lagrange multipliers for both the constraints, both the objectives have to sum to C. So you can do this, right? They take the Lagrangian and differentiate this with respect to xi and see that it will end up giving mu I star plus lambda star to be equal to C. Okay, so this is one additional constraint that we got with what we will use. Now we will have to formulate the dual problem. Formulating the dual. So to find the dual now, which is a function of both the Lagrange multipliers mu and lambda, we will have to consider the infimum of the Lagrangian, which is a function of w, b, xi, mu and lambda. This infimum is with respect to the optimization variables in the primal problem, which are w, b and xi. Okay. Now we already know what the optimal WB are, which we can just plug in there. Okay. Now observe, just like we put the constraints in the previous case on while constructing the dual, right. So you observe that L has a term, L has this particular term, some C minus mu I minus lambda times psi I. So where do we have this term? It comes from here. So there is a C times sum of xi I here, right, and there is a lambda times xi I here, the sum is over same I, okay, and there is a mu times xi I term here, the sum is over I again. Do you see that? So if you combine all these terms, you will have a sum, okay, of xi I, okay, multiplied by C minus mu I minus lambda I, correct. So this term is there. Now if again, just like the previous case, if you do not draw this to 0, then this infimum can go to minus infinity. So we will have to constrain it to go to 0. So we will have to ensure that this is put to 0 as a term that needs to be made 0 to avoid the trivial solution, which implies we have mu I plus lambda I, this to be equal to C. Correct, right. So with this, now the dual problem will be as follows. We need to maximize over actually with this constraint and making w, b, xi to be the optimal values, you will have to plug that into the Lagrangian and show that this q mu, okay, will now become a function of mu only, I mean, which is very similar to the dual problem that we had previously. Okay, again complete that algebra. And am I clear? So what I am saying is that put this constraint into the Lagrangian and put substitute W star and B star, the optimal W star and B star to the Lagrangian and expand it out. Okay. If you do that, then you will end up getting this particular dual problem, which I will write now, which is minus half some more I some more j yi yj mu I mu j xi transpose xj such that mu I is non-negative and if lambda I also to be non-negative. See, so this dual problem had to be a maximization over lambda as well, okay, but the objective function itself becomes independent of lambda, so it comes up in constraint, you can just ignore that, okay. And fine, I am using the same symbol for xi and let me not do that. And we have that C is equal to mu I plus lambda I, correct. Right. Now the problem, the objective function is independent of lambda, right. So now if, I mean, there is no need why we should have a lambda here, we can subsume this lambda to be non-negative here in this constraint itself. How do we do that? So to take out lambda, modify the constraint as so make your force mu I to be with less than C. Just a second, if I make mu I to be less than C, right, then I can give away this lambda to be greater than 0, correct. Now the final problem now will be exact same maximization such that mu I is greater than 0 and it is bounded between 0 and C. Come again, lambda here, correct, yeah, we will not have a lambda here. See, now this is the elegance, when I told you, right, finally we are still solving this problem. This problem is still quadratic in mu, okay, with linear constraints on mu. There is only one additional constraint that comes up, that this mu has to be bounded within C, that is it. If we do that, then we are implicitly saying that there is a slack and the sum of that slack is controlled by the C. The question that you asked, right, where is the effect of C, this is where it is. So now how do we choose this C in practice? It is a hyperparameter. Okay, in fact, libSVM will give you an option to grid search over the C. Choose different values of C. How do we, I mean, how do you select hyperparameters? You already know that, you know, look at the performance on the validation data and then do it. So C is a hyperparameter. When it isn't it so elegant? So for all that we did, introduce a slack and all that, finally the optimization problem that we will be solving will exactly be the same, but with one constraint on the variable or the optimization variable that we have. We are simply saying that find my C such that it is less than, find my mu such that it is less than a particular fixed value, and that fixed value appears as a scaling factor, okay, in the sum of the slack variables in the primal problem. We have a linear coefficient for B also. We should also make that 0. Yeah, that's also there. That's there. Which came in the previous case, right? That's there. Yeah. So it is here. You are saying, you're talking about this term, right? This term had to be made to 0. Correct. I assume that it is similar to the previous one. Yeah, that's correct. Fine. So finally, what happens is when you solve this using SMO kind of QP solvers, put a constraint on your mu and you are already assuming that there is a slack. Okay. Yeah.
the dual, and then we that we have to make some term 0. That
Mm.
seems like artificial in the sense that like for every function we set something to 0.
Well, yeah. So that's a standard practice in optimization theory. So why are we doing that is as follows, right? See, if your optimization or some variable without putting some constraints leads the problem to a trivial solution, right? You don't want that. It will definitely take you to that trivial solution. What's the point? You put a constraint to just to avoid the trivial solution. That's it. It's a standard practice in optimization. So if you have if your optimization problem leads to a trivial solution, avoid it by putting constraints.
One thing is that when we wrote the differentiation, we also get C as like mu star plus lambda star. So
Sum of mu star and lambda
so
star.
you have
Correct.
the constraint somewhere there also. Okay? Like
No, we get it actually in the dual problem too. That constraint exists. It comes up like this.
that right instead of like setting it 0, like if you just replace.
No, this one. See, you are talking about it appearing in the see. Okay, you're talking about this one, right? This one is because xi can be chosen in such a way that it goes to trivial solution. We want to avoid that. See, please note that the dual function is an optimization over your primal the variables in the primal problem. It is not over Lagrange multipliers. You understand? So, any constraint that you are putting while you are constructing the dual function has to be a constraint on the optimization variables of the primal problem, either W or B, or in this case xi. Okay. Now, this xi can be made to take the value of minus infinity, and this q mu can take minus infinity. We do not want that. We do not want that. Therefore, you drive this term to 0. And now because you drive that term to 0, that this entire Lagrangian now will become independent of xi. That is how this dual function still be the exact same form as that of the dual function in the non-slack case, because you are completely removing the dependence on xi here. Got it?
So my just the question was that when we differentiated with respect to xi in the original KKT,
Hmm.
and we got the same like C, that C is equal to mu star plus, but there is a mu star that already is like the optimum.
Correct.
So if is there a relation between like setting this to 0 and the condition that we get here?
Is there a relationship between them?
Because that happens.
I understand. Yeah, there is, right. I mean, if I say that mu I plus lambda is equal to C, choose a mu I star lambda I star such that it is equal to C, then this term is anyway going to 0. Yeah, correct.
That's for star. That here we are studying for every.
Correct. But this is while constructing the dual, not while optimizing, but that is while optimizing. Right. So, this is the, see, formulation wise, you got the exact same problem with an additional constraint on mu. Okay. Okay. So, this is about max margin classifier with a slack formulation. In fact, it is very interesting that given a problem, we will not even know how many slacks were chosen and what values slacks have for every data point. We will not get to know that at all, because finally when you solve this, what you will get is a mu. Okay, a mu and then a W and a B. With a W and a B, there is no access to xi at all. You can control xi only through the C. We will not know what slacks are, when we solve the problem. It's very elegant that way. Okay. So let's finally, there is one final case that we have to look at. So SVM with the kernel function. We will stop here and continue in the next lecture.